Hello everyone, welcome back again on our Big O playlist in computer science. Today we will again be solving one other question on time and space complexity. Before we basically look into this question and how to solve this, maybe we can go through the recap of what we have learned so far. So let's see what we have learned so far. So first of all, very briefly, let's understand what is the importance of big O notation as a whole, right? So we learned in first part of this playlist that big O notation is really a useful concept to analyze the complexity of a given algorithm. So when we say complexity, it means that how much time it is going to take for an algorithm to run, which we call as time complexity. And the other one is how much space or memory a given algorithm is going to take when it will be executed. So that is referred to as space complexity. Then we basically uh, discussed terminologies which someone might not be aware of. For example, algorithm. So what is algorithm? So algorithm is actually a series of steps which we have written in any programming language to solve a particular problem, right? So algorithm, we can correlate it to a function or a method which is doing something. And that function or method can be implemented or can be written using any programming language. And once we have written the algorithm or the series of steps to accomplish a particular task or to solve any problem, then we basically look at its efficiency, its runtime or memory efficiency by uh, basically thinking of what which all steps we are doing, and once we determine its time and space complexity, then we are good. Then we can think of how to optimize it better if there is a way, right? Then we also looked at a few other terminologies while using this concept of big O notation. So one was that we can actually have a big O, the other one is big omega, and one is big theta, right? So big O describes the upper bound on the runtime. So likewise, big omega describes the lower bound on the runtime. And then big theta is actually when big O and big omega is same, right? So it is the tight bound on the runtime. Then we gone through some examples, and then we also learned that whenever we are determining or somebody is giving us an algorithm and we have to determine its runtime, then we will look out for the tightest bound on the runtime. So tightest bound in the sense that how much max time a given algorithm can take, right? And then we looked at best case, worst case, and expected case scenarios for a given algorithm, which mainly depends on the data which we have been provided, right? So for example, we talked about, let's say there is a let's say if I put a uh, example here. So let's say we have an array, right? This array has 1 2 3 4 5. So and then we are given, let's say, 5, right? So we are given two things. One is this array, and one is that we have to find this number. So let's say if I am basically uh, if I have written an algorithm which is a linear search, right? So in linear search, what we do is we basically start a for loop on this index, and then we keep going down one by one to check whether the element at given index is matching this number. So as soon as it matches, then it returns its index. And if we have not found the given number in this array, then we return -1, right? So in that case, the best case would be that we are given this array and we have to find a number. Let's say rather than 5, we are given a number as 1. So what will happen in our linear search algorithm is that, so it will go with the first index where I is equal to 0, right? So array on 0 is basically 1. Then we check whether this 1 is matching the given number. 1 is equal to 1. It's true. So it's true means it will return, right? So return its index, which is 0. So this is the kind of best case scenario, right? Because we I we started iterating through this given array, and at the very first index we found the number. So it's kind of best case scenario, right? So we found the number at the start of the index. But then what is my worst case scenario? So worst case scenario, let's say now this time our algorithm is still the same, right? We haven't changed anything in the algorithm. If we are talking about worst case scenario, it's just that we are given this time number as, let's say, 5, right? Or maybe let's say 6, which is not there. So in that case, we will iterate through I is 0, then 1, then 2, then 3, then 4, right? All the indexes of given array, but we haven't found the matching number, which is 6. So in that case, it is the worst case scenario because we have gone through all the elements, but we haven't found the given number or the number which we want to match. So that is the worst case thing. And then the expected case is usually the average case scenario, because usually whenever we are given an array or when we are given this number, so on a given on an average day, our array will be like randomly distributed. It will not be like always like 1 2 3 4 5 or 5 4 3 2 1. It will be like mix up. Mix up means like maybe let's say 2, then 1, then 3, then 4, then 6, and 5, something like that. So it will be quite random, or maybe very distributed, not in the increasing order, not in the decreasing order. So usually in the expected case scenarios, let's say in case of this example linear search, so maybe we will find the number most of the time in the middle of the array, right? So that is kind of the average case or expected case scenario. So overall, what we have talked about here is why to learn this concept, what is an algorithm, what is the use of big O notation, which are the related terms big O, big omega, big theta, what is the tightest bound on the runtime, what is the best case, worst case, and expected case for a given algorithm. And then we know that what is time and space complexity at this point of time. So time complexity is runtime, how much time a given algorithm will take in terms of size of the input. And then space complexity is how much space it is going to have in terms of size, input size, right? Then we looked at some common complexities or common patterns, which is like order of 1, order of log n, order of n, order of n log n, order of n square, order of 2 raised to the power n, and many more. Then we looked at some other examples of amortized time, right? Which is the average time over a long period of time. And the example we talked about it is dynamic resizable array, which is an array list. And then basically, if I just clear this out, right? Then basically we looked at the login complexity, right? So in this example, what we did is, we talked about the linear search, right? So in linear search, my algorithm is going to take order of n time complexity, or linear search algorithm runtime is going to be order of n, because we have to traverse through the entire array to find a matching number. But then we talked about another algorithm of binary search, where the binary search is like, if my given array is sorted 1, 2, 3, 4, 5, and I have to find 5, then I do not, so I start in the mid, and then if I do not find it in the mid, then I go to the upper half, because this number is 5, which is greater than the mid. So we know that we just need to go to the right side values to find the matching number. We do not need to go to the left half of the array. So basically in binary search, we reduce our time, our range of values by half each time. So eventually it comes to log n time. So it means that uh, if we are given, let's say, I would say, if we are given 16 numbers, for example, right? So if I do log 16, so log 16 is log 2 raised to the power 4, right? So I will just take 4 steps. So login, so if my n is 16, then my login is going to be 4. So it means in the 4 steps, I will find whether the number is there in the given array or not. So basically, we talked about this login complexity and with an example of binary search. Then we talked about recursive algorithms and some sample codes, wherein, for example, uh, if I remember the example correctly, so we were given n and we were recursively calling n minus 1 2 times. Then we were calling this again n minus 1, n minus 1, like that it was being called. And eventually we found that the complexity over there is 2 raised to the power n, right? Then we talked about two important points while determining complexity. One is like dropping the constants, which was meant by that if we found our complexity is coming like this, order of n plus 2, so we can drop the constant and it is going to be order of n, right? And likewise, we basically also learned another important point is dropping the non-dominant terms. So what it means is that if our complexity is coming out as order of n square plus n, then we can just drop the non-dominant term and the complexity we can say is order of n square, right? And then we looked at some examples and questions in the previous part in this playlist. So please feel free to go back to those parts, and you can listen to those parts in maybe in 2x speed, because sometimes or most of the times I am speaking very slowly, maybe just to explain the concepts very clearly, or maybe it's my habit like that. Okay. So with that, let's maybe go through another example or another question in this part. So we have to determine the runtime of this code, right? So in this code, what we have given is we have given two arrays, array A and array B. So what we are doing is we have we have three for loops, this one, and this one. So in the first for loop, we are going through this array A one by one till we go at the end of this array, right? So let's say if my array A is like 1, 2, 3, right? And then let's say if I have another array B, which is my 4, 5, 6, right? And then I just have two arrays, right? So what I am doing here is in the outermost for loop, I go one by one for each index 0, 1, 2, right? So I goes from 0 to 2. So I is 0, I is 1, I is 2. Then for each index of outermost loop, I go to second for loop from j is equal to 0 to this till the entire length of array B, right? So for I is equal to 0, j goes from, so this is my second array, j goes from 0 to 2, right? In this case as well 0 to 2, and in this case as well 0 to 2, right? Because first time when I is pointing to this, then j goes from here to here to here. Again, when I goes to this 2, then again j will follow the same pattern of 0, 1, 2. When I becomes 3, when I becomes 2, then j becomes again 0, 1, 2. It will go, right? So it means that if my array A has length of A and array B has length of B, then this is the total number of times my first and second for loop will result in execution, right? A is to B times. If A is the length of array A and B is the length of array B. Because if you look at the third for loop, so in this for loop, we do not have any dependency on I or J. And in the sense that we are not iterating through this array A or B in the third for loop. This third for loop is kind of constant time it will run. It will run from k is equal to 0 to 100,000 times, right? So I can say this is like order of 1. It is in constant time. But then this thing will run order of A is to B times. And that is what we are doing. So overall, my complexity is going to be order of A times B plus order of 1. Finally, we can drop the constant. So A times B. So ultimately, my answer is going to be A times B. And please note that you can never say it's order of n square, because we do not know what is the length of array A and what is the length of array B. So array A might have, let's say, n elements, and array B might have, let's say, m elements. So in that case, it depends on n is to m. But definitely, if both array A and array B has n elements, then eventually it will come out to order of n square. But that is if we are assuming that my array A and array B has same length or same number of elements. Okay, so this is just the few rough work slides I have created just to see if I want to explain something here, but I think we are mostly done with it. So it's going to be A times B. Feel free to drop any comments if you have on any of the query for this part or maybe for the previous part, and I will try my best to answer it. With that, happy learning. Thank you.